So let's continue our study of limits by examining how to find a limit from a table. Now we're still going to be looking at input and output, but rather than a graph, we're going to compare input and output on a table of data. Our objective, the student will be able to define and calculate limits for functions given in tabular form. Now, as with polynomials, limits of many familiar functions can be found by plugging in at points where they're defined. And plugging in can often be represented by inputting x and outputting y, and listing the information out in the table. We're going to be able to do this with trigonometric functions, exponential, logarithmic, and composites of these functions. Creating a table is a way to determine limits using numeric information. We'll create a table of values in which the input values of x approach a from both sides. So we'll have to be both left and right, or less than and greater than a specified x. Then we're going to determine if the output values get closer and closer to some other real value. It's really just the same thing we're doing in a different form. Now, when we're doing this, we're going to be choosing input values that get infinitely close to the desired input x. Getting close means we do not pick x values in constant increments. We're not going to pick -2, -1, 0, 1, 2, the way you would have done back in Algebra 1. Since we want to get infinitely close, we have to keep reducing our increments. So 1.9, 1.99, 1.999. So you just see how each time I'm still getting closer and closer and closer to 2, but I'm not actually reaching it. And this part right here would represent being less than or left of 2. So less than or left. Now on the other side, I'm going 2.1, 2.01, 2.001. I'm staying just a little bit bigger than or to the right of 1. So just a little bit greater than or to the right of 1. And we're going to do this from both sides if it's a two-sided limit, or just from one side if it's a one-sided limit. As we're looking at our table, we're also going to try and determine if our location represents a point, a step discontinuity, a removable discontinuity, or an asymptote. Now, it will be challenging at times to determine the difference between a step and a removable, and so this might come later on with more practice. However, determining a step discontinuity and asymptote should be fairly clear. So here's our first example. As you look at our values of x, it seems we're approaching 2. We're going to approach 2 from the left on this side and 2 from the right on the other side. And as I'm looking at 2 from the left, I notice here that my output, so the output on the left side is 3. So we'll have the limit as x approaches 2 from the left of this function is 3. When we look at the right side, we see coming in from the right, it appears our output values are actually getting closer to 0, because it looks like we're always adding more zeros. So in theory, it'll eventually be 0.000000. So we can say that the limit as x approaches 2 from the right of the function is 0. So what we have in this case is a left limit that is different from the right limit. And whenever the left limit is different from the right limit, that's a pretty good indication, that we have a step discontinuity going on. So we're going to say that in this particular case, this table represents a step discontinuity. Our next example, still approaching 2, and let's start by coming in from the left side. And as we approach 2 from the left, it seems that our output values are getting closer and closer to 3. So we are going to say that the limit as x approaches 2 from the left of this function is 3. Now, looking at the right side of 2, as we come in from the right side, it also appears that our y values are getting closer and closer to 3. So we have the limit as x approaches 2 from the right of this function is 3. So we notice in this case that our left limit and our right limit are approaching the same thing. So we can say that the limit as x approaches 2 of our function is 3. But this could represent a point, or it could represent a removable discontinuity. So what we need to do in a case like this is understand whether our specific value is in our domain and if that value equals the limit. So if we know for sure that f of 2 is 3, then we're going to call that a point. However, if there's information such that f of 2 is not 3, then it's going to indicate a removable discontinuity. So you have to be careful with that when you're doing tables. Make sure you pay attention to whether or not the value and the limit are the same. All right, still approaching 2. So now let's look at our output values: 10, 100, 1,000, 10,000. If we follow that pattern, we can assume that we'll have 100,000, a million, 10 million, and so on. So it appears that in this case, the limit as x approaches 2 from the left of this function is heading towards infinity. Looking at the right side, negative 10, negative 100, negative 1,000, negative 10,000, negative 100,000, so on and so forth. So now we can assume here that the limit as x approaches 2 from the right of this function is negative infinity. We have one side heading towards positive infinity and one side heading towards negative infinity. So one side's going up forever, one side's going down forever. All of this implies that we have, in this case, a vertical asymptote. So in this example, we are going to determine the limit as x approaches 0 of sine of x over x. So our function in this case is sine of x over x, and the specific x value we're approaching is 0. So the first thing I want to have y'all notice is that if we were to directly plug in sine of 0 over 0, we would get a 0 in the denominator, and we can't have that. So what this tells us is that x equals 0 is not in the domain. It is not in the domain. So this cannot be a point. We know that for sure. So now let's take a look at our output values. So what I would like for you to do is go to your calculator and put sine of x over x in the y1 in your calculator, and then go over to the table and put the x values I have listed for you here into your table, and then fill out your y values, and then we're going to compare them. All right, so here are the values I came up with when I plugged all the numbers in my calculator. So starting left of 0, I noticed that my output values are getting closer and closer and closer to 1. So I'm going to say that the limit as x approaches 0 from the left of sine of x over x is going to equal 1. So now looking at the right side, my right values are also approaching 1. So then we can say that the limit as x approaches 0 from the right of sine of x over x is also 1. So then what we can say, because both the left side and the right side are equal to 1, is that the limit as x approaches 0 from both sides of sine of x over x is equal to 0. And since we've already said that x equals 0 is not in the domain, this means that we have a limit, but we do not have a value. Therefore, what we're going to have in this case is a removable discontinuity. So let's go ahead and take a look at the graph and see. So here's a graph of sine of x over x just on a small portion of its domain. And you can't tell because sometimes on calculators and on graphers you can't see, but according to our algebra analysis and our common sense of what we've done, there should actually be a removable when x equals 0 and y equals 1. There should actually be a removable. So here's our graph, and we have our limit correct. What you may or may not remember is that we called the limit as x approaches 0 of sine of x over x a math fact, a limit fact last year, one that you needed to have memorized. And I advise you to memorize it again. We will be dealing in about our third unit with another way of solving this problem, but for right now it's going to be such a common trig limit, I highly advise you to memorize it. So here's our next example. We are going to create a table of data to determine what the limit as x approaches 9 of root x minus 3 over x minus 9 is. So please go ahead and pause your video, fill out your chart, and then we'll go through it. All right, so here's my chart. As I'm approaching 9 from the left, I'm looking at values slightly less than 9, so 8.9, 8.99, and my output values go 0.167, 0.1667, 0.16667, so on and so forth. So they're approaching 0.1666 repeating. Now when I'm right of 9, my values are going 9.1, 9.01, 001, getting closer but still slightly bigger. And notice that my output values are also approaching 0.1666 repeating. So putting all this together, what we can say is the following. Ooh, did not mean for that to happen. Let's try this one more time. All right, get my little box here. We will say then that the limit as x approaches 9 of root x minus 3 over x minus 9 is 0.1666 repeating. Alrighty. I also can tell by looking at my function, if I was to plug in 9 directly, I'd have a domain issue. So we know that f of 9 does not exist. So if we have a limit but not a value, this means we have yet again a removable discontinuity. Now I promise you they're not all removables, but those are the quickest ones to do tables from, and you'll see some various cases going on in your practice problems and in some of our class discussions. Here's a picture of our graph. 9 will be right about in there. If I go up and take a look, and then backtrack all the way, it should be roughly 0.1666 to help you sort of take a look at that. You can see that it backtracks to something slightly less than 0.2. If I was to kind of do this properly, that'd be about 0.1, that'd be about 0.15, and so that would be slightly around 0.1666 repeating. Hope that helps. So here's our last tabular example. Determine the limit as x approaches 1 of 1 over x minus 1 over x minus 1 using a table, and then confirm graphically. So just like the others, please pause, fill in the table, and then we'll look at the results. So here's what I came up with. As we're dealing with the left side, so being less than 1, I notice that my y values go towards -1. So when my x's are less than 1, my y values are approaching -1. So I'm going to say then that the limit as x approaches 1 from the left of this function is -1. Now on the right side, as my x values or my input values are bigger than 1, my output values are also approaching -1. So we'll have the limit as x approaches 1 from the right of our function also approaching -1. So I hope you just literally see how I'm just making sure my output values get closer and my input values get closer as we go. So putting all of this together, what we are now able to say is the following. Draw my big old box here. We will say then that the limit as x approaches 1 of 1 over x minus 1 over x minus 1 is equal to -1. We also know that if we plugged 1 in directly, doing a domain check, this does not exist. I probably shouldn't do a double knot. Let me erase that. I'm going to do an imply symbol because technically you don't equal does not exist. So f of 1 does not exist. So we have a limit, but we do not have a value. So this tells us we should have a removable discontinuity. And we will go and take a look at our graph to see if that's true. So here is our graph. Let's take a look at it. Please notice that's marked at 10, which means each of my lines is marked by 2. So this tells us that this is 2 and 1 is right there. You can't quite tell on the graph, but according to our work, let me actually kind of get down here. Right there should be a removable discontinuity. It's just not going to show up in our graph.